Okay, so here's the solid sphere, and the inner radius is, this is 2a, and the outer radius is 2.4a, and we're going to consider a point somewhere here. Now this has positive charge. The solid sphere, the non-conducting sphere, has positive charge, and these charges create electric field, and these electric field lines are radially outward. So I'm going to draw these electric field lines like this. But we know electric field inside a conductor is zero. Whether it is charged or not, the electric field inside a conductor is zero. So what that mean? These electric field lines will not extend beyond this point to this direction. So you don't have electric field inside the conductor. If you consider Gaussian surface, just outside the this inner sphere, like this is the Gaussian surface I'm going to consider, and you can see there's no flux going through, or no electric field lines are going through this Gaussian surface. What that means? The net flux going through this Gaussian surface equals to 0. From the Gauss law, we know the net flux through any Gaussian surface equals to the charge enclosed by that Gaussian surface. But since there's no flux going through this Gaussian surface, charge enclosed by this Gaussian surface equals to 0. But the solid sphere has some charge, that's Q. Then what should be the charge on the inner surface of the the spherical shell? That should be minus Q. When you add these two charges together, plus Q and minus Q, the net charge is going to be 0. So if you consider any point outside of this conducting sphere, the electric field going to be 0. Why? The charge enclosed by any Gaussian surface which is bigger than this spherical shell going to be 0. So no flux going through that Gaussian surface. So charges, electric field is 0. So here the answer is 0 here, the electric field is 0 here, and we found this electric field. And how do you get the net charge on the inner and outer surface of the shell? The net charge on the inner surface of the shell is minus 5 picocoulomb. Outer surface, that's 0.